The next speaker, okay, I'm going to try really hard to pronounce his name correctly here. The next speaker is from Instacart, and his name is Tejaswi Tenneti. Okay, Tejaswi Tenneti. Okay, he's giving me a thumbs up. And he's a senior manager of algorithms and machine learning from Instacart, and he refers to himself as the search guy. All right. Okay, well, he's still loading up here. So I guess that means I'm going to have to sing and dance. There's a reason I'm a left brain quant. I don't sing or dance. Oh, here he comes. Good. Thank you.
Hey everyone, I'm Tejaswi. I'm from Instacart. Today I'll be talking about some of the work that we do inside our search team. A bit about me. I'm currently leading the search team for machine learning, search and discovery for machine learning inside Instacart. Our team works on interesting problems such as neural text modeling, user intent understanding, multi-objective ranking, and so on to power search and autocomplete. Instacart, for those who are not familiar, is the leader for online grocery delivery in US and Canada. Our mission is to create a world where everyone has access to the food they love and more time to enjoy together. Coming to the topics I'll be talking about today, I'll first start with an overview of Instacart's search architecture. Then I'll talk about the scale of our data and try to convey why building performant ML models for Instacart's use case can be quite challenging. I will talk about two use cases, which will illustrate how we try to overcome some of the challenges in the last 1 year. Finally, I'll talk about some lessons learned. Right. So here is how the architecture of search looks like right now. So we have three components: query understanding, retrieval, and ranking. These are some things that you typically see in modern search engines. Query understanding is really about extracting personalized user intent signals from the current context with the search query. And we use these signals to match the most relevant products that the user is looking for. And finally, we have several stages of ranking that the products go through before we present them to the user, right? There are a couple of critical ML models that we work on. Query classification, which is mapping a search query to one or more product categories in our taxonomy. Query tagging, which is understanding what are the important entities that are present in the query, like brands or product attributes, dietary attributes, and so on. Ranker is like, hey, we have like a ranker that optimizes for like multiple objectives. I'll talk about that in a bit. Search embeddings is a model that we are very proud of. This has helped us solve the cold start problem and really generalize across retailers. This is something that I'll talk about in the next slide. Cool. Coming to the scale of our data, one of Instacart's key component in our vision is to be like a very strong partner to all the retailers that users love and use across US and Canada. We currently partner with like 800 national, regional, and local retail brands spanning across 70,000 stores across 5,500 cities in the US. So totally, we're talking about like around 1 billion products that our search operates over. Now, I agree that billion isn't like a mammoth scale in 2022. However, the diversity of the products that our retailers carry is what makes this problem very challenging. So our retailers carry products ranging from traditional grocery to pet products, beauty, alcohol, and so on. So all of this makes it very challenging to create ML models that generalize across all of these retailers, especially with like a small machine learning team of our size. Finally, coming to the scale of our queries, it used to be at a very manageable scale before 2020. But as our user base grew, so did the range of queries that users issued on our platform. Users started entering very broad queries like lunch to very medium intent queries like low-calorie drinks to very, very specific queries like, say, frozen yeast rolls. So it became very important for us to understand these very tail queries as new users started coming in into our platform and making sure that we keep our retail partners who are coming in new to the platform very happy, right? So at a macro level, what are some of the challenges that we tackled, right? So the first one is generalizing across all retailers. So, like I explained in the previous slide, the scale at which we operate lends to like a lot of diversity in the inventory of our products. So, for example, queries such as Apple can be very ambiguous depending on the retailer that the user is actually searching in, whether it's a traditional grocery store where the user is looking for fruits versus a general electronics store where the user is looking for the brand. Similarly, queries like vanilla can also be like very ambiguous. The user could be looking for the name of the product or the description itself, like for example, vanilla scented like beauty products at at Sephora or so on, right? So large search teams, like some of our counterparts like Walmart and Amazon, solve this problem by dividing and conquering. They build specialized ML models for each of the verticals. Unfortunately for us, we don't have the size to build this solution, so we had to innovate in terms of ML models that we built so that we could generalize across all of these use cases and so on, right? Next, I'll talk about the cold start problem that we have. So for understanding what are the most relevant products for a given query, let's say they're very popular queries or very popular products, you can end up relying on either keywords that are present in the search or historical user signals like click-through rate and so on as such to determine this. However, this assumption quickly breaks down once you get to not so popular queries or not so popular products, right? So what we had to do was develop like a holistic understanding of the queries and the products so that even when these sparse signals are missing, we could still show the most relevant results to the user, right? This is especially important for new users since new users tend to enter more complex queries than existing users. Right, so yeah, talking about our users also have like a broad spectrum of needs that we serve across. So starting from the queries that they issue, maybe they're very broad queries to very narrow queries. Their shopping intent can also diverge from being very like, hey, I know the exact product that I want, versus I'm in like a discover mode where I'm open to new products and so on as such, right? Similarly, there are users who shop for a very narrow set of categories versus users who are like exploring all the time or are like receptive to new ideas. For example, if you show them like a recipe, they tend to interact with that, right? Finally, we have a challenge in terms of like, what are the goals that we serve for our users versus our retailers versus platform goals, right? So search for like e-commerce company like Instacart cannot be just about relevance, right? We are not Google. Why is this the case? Simply put, relevance alone is not correlated with revenue. Similarly, as we've seen in other recommender systems and use cases and so on as such, more diversity of the products as such rather than showing the most relevant products and so on leads to long-term user satisfaction, which is what we really want. Therefore, our search had to evolve from being like this relevant shop to like a marketplace where we increase the pie by optimizing for multiple objectives, right? Now I'll talk about how we solved a few of these challenges. First, I'll talk about the model that we used to do the dense retrieval and solve the cold start problem for us, as well as the problem of generalizing across all retailers. Great talk, Sam. Like we do something very similar to what he just described earlier, right? So we have this dense retrieval layer, which means we do keyword search in a separate system from and index our products also into this, what is called like a approximate nearest neighbor service, very similar to the talk earlier. So we built a model that gives us this dense and unified representation of both user queries as well as the product so that we can match user queries to products even when the user engagement signals are sparse or sometimes misleading, right? So items, which is the name of our model as such, is able to provide us like a very reliable measure of relevance just beyond the click-through signals that we are generally used to, right? As you can see from the figure on the right or your left, so basically like if you compare click-through rate as a signal for relevance versus items as a signal for relevance, what we found out was that click-through rate has like diminishing returns because users tend to typically engage with items on the top that you rather than any items that are down the list and so on as such for any given query. So as you go down the ranks of the products that you show for like a response, you find that even like more relevant products as such, even if the product is very relevant, if it is down the ranks, users don't engage much with that. Hence, the click-through rate signals are like almost absent and very sparse, so we cannot rely on that. Items are transformer-based embeddings model solved this problem by essentially like providing like a uniform signal by using only like text features and no engagement features and so on as such, right? Additionally, we were also like able to understand the nuances across different retailers by directly encoding retailer-specific information. What is the kind of retailers that the query is being done in and so on as such, directly into the model. Therefore, we could understand differences between like a query like snacks in Kroger versus a query like snacks in like, let's say, a niche Asian grocery store needed to show very different results because the user needs in those stores are very different, right? Again, I don't have the time to talk about the model right now, but please check out our paper in Sigair Ecom this year for more details, right? So yeah, what are the key takeaways, right? So investing in like a separate semantic relevance model has helped us solve the cold start problem instead of trying to do it all with a single model. Second, we were able to sufficiently generalize across different retailer types without having to build like individual models like most companies with big teams do. Cool. Now let's talk about the another two problems that we usually try to solve. So the first is the challenge of catering to a broad spectrum of user needs, and the fourth problem that I talked about is balancing this user versus retailer versus platform goals and so on as such. We have many levers to address these problems, but I'll now focus on how we use Autocomplete to solve this, right? Auto-completing users' query when they start typing in the query and so on as such is like a great way of making search journey much more efficient. It assists the users in like expressing their intent very, very clearly and helps them explore like a wide variety of options, right? So autocomplete for us is like two steps. So one is the recommended searches. Even before the user starts typing in the queries and so on as such, we tell them, hey, these are the queries that you probably will be interested in like a personalized manner. And the second one is the type head functionality. You're trying to complete the user's query, right? So to make autocomplete suggestions very appealing to the users, what we did is like all of the candidates for the autocomplete, we generate them from past user searches so that the suggestions themselves have like a rich, natural feel to it instead of showing some canonical forms of like categories or brands that other autocomplete systems try to do, right? So as we started doing this and so on as such, the engagement rate of our autocomplete started growing more and more. So we applied clever tricks on making sure that the limited real estate that is there on autocomplete and so on as such is we utilize that fully by deduplicating any semantically related queries or semantically similar queries and so on as such. We also increase the coverage of autocomplete across multiple retailers so that all retailers have great suggestions. So what this led to was an increase in autocomplete engagement rate as like a surface. And we were like, hey, you know what? Users love this surface. Why don't we try to see if we can have like a principled ranking solution for this instead of the popularity-based sort that we usually have. So we set out to build like a simple logistic regression model with like very simple features. So the first feature is what we call as the autocomplete conversion rate. Given a prefix and a completion, we are trying to predict the probability of user completing to this particular query. We also use the skip rate, which is essentially like how many times did the user see this query and not engage it with it all. We look at normalized popularity. We looked at whether the suggestion has like a thumbnail associated with that or not, and so on. And after we deployed this model in production, we saw fantastic results. Not only did people engage more with autocomplete, but we also saw an increase in basket sizes, which means more revenue. We were like, this is fantastic. We found like a new lever to drive more revenue. So let's keep improving this model and start to see more revenue gains. So that worked for a while until it did not. So we saw that, hey, we started users love it, users are using it more and more, but that's not translating into revenue. So we asked ourselves a few important questions. Can we use autocomplete to shape user search behavior? Can we use it to drive incremental basket sizes and more revenue? Can we use it to influence users to try out new categories of products that they haven't probably tried before, right? So in order to do this, what we did was we built individual models. So if you think of all of these questions as individual objectives that we want to optimize for, so we built individual models for these objectives. So in this example, like we have two objectives. So one is increasing the autocomplete engagement rate, and the other one is increasing basket size through that. So we build two different models, and then we take like a model fusion approach where we combine both of these objectives in like a simple label aggregation fashion or like a model aggregation fashion, right? And after we deployed this new model into production, we saw fantastic results. We were like, hey, you know what? All of our theories were right. We definitely could influence the user to efficiently finish their search, but at the same time, we could also influence the user to increase their basket sizes and buy more with us. So we started taking this layered approach where the first set of layers of models are like really about different objectives, and then we have layers on top of that, which is these models are like really about balancing all of these objectives. So right now we are building models which will make sure that there is enough diversity across all of these objectives. So we have diversity across making search more efficient, we have diversity across making more money, we have diversity across diversity itself, and so on as such of the suggestions and so on, right? So this worked like really, really well for us, and yeah, what are the key takeaways, right? So one is autocomplete can help us understand our users' needs better, which is like serving the broad spectrum of user needs. At the same time, it can also be efficiently used to shape a user search behavior and help us balance between user goals versus platform goals and so on. So yeah, we're really looking forward to making more strides in this case. Now I'll switch gears a bit and talk about a few operational challenges that we encounter in our team. So the first one is about data quality. So no-brainer, or ML models rely on a lot of data to produce accurate predictions. Most importantly, product metadata is one of the most important signals to us as such. Each product roughly has like around 100 attributes that can be associated with this product. Now, it's very, very challenging when you have like a billion products spread across all over, and all of these attributes are coming from like disparate sources, like retailers giving us some data, CPG brands giving us some data, and so on and such. It's very hard to understand the accuracy or evaluate the accuracy and coverage of all of these attributes, right? So we try to invest in human evaluation data, because evaluation itself does not have any ROI. It would constantly get deprioritized. People were like, how much revenue is evaluation gonna make, right? 0. So it would get deprioritized. I will move on and then talk about like how we solve this problem and come back to the next problem. So after a while, dilly-dallying with vendors who would evaluate data for us or provide data for us, we were like, hey, it's time to invest in our own automatic product attribute extraction as such. So what we did was we broke down this problem into like 3 steps. Right? So the first one is attribute identification, which means for a given product or a category of product, we need to first identify what are the attributes that are applicable to that, right? So for example, for milk, what are the product attributes that are applicable to that? Maybe like fat content, brands, and so on and such are the product attributes, right? And we do this product attribute extraction by using domain knowledge experts who know these products in and out and so on as such. We also use external databases like Wikipedia and so on as such and try to extract these attributes or try to identify which attributes should be associated with products. And we also use like raw product data. Like sometimes just looking at the name, you'll be like, this is an attribute that needs to be associated with the product, right? After that, we go on to the actual extraction step. So this is like a multi-module, right? I mean, so the first thing is for very easy attributes like kosher or vegan, we just have regex patterns from product names and so on as such to say, hey, is this product kosher or not? Or even from the images and so on. For more nuanced ones, right, like flavors and so on, right? Like sometimes cherry or chocolate can be like a color versus a flavor and so on. So we use BERT-based named entity recognition models in order to really understand the context and extract more nuanced attributes, right? Finally, normalizing the attribute values is a very important step. So if you take something like milk, it can come in different metric systems. So one could be fluid ounces, another could be like gallons and so on. Downstream machine learning models, which will consume all of these feature values and so on as such, it would be better if we normalize all of them into the same metric system, right? So what we did was we did this third normalizing step and so on. And all of this like paid off really, really well in terms of like improving data quality for us, right? Now, I don't think I can go back a bit, but I would also like to cover some of the challenges that we have with architecture, right? What happens is like in a typical tech stack, machine learning tech stack, at least for search systems that I've seen earlier, there are two tech stacks at least. So one is a Python-based tech stack that machine learning engineers generally operate over, and another is a search backend. This happens to be either Java, if you're lucky, or in our case, it is Ruby on Rails, which is a language that no machine learning engineers are like very familiar with. So although we have like well-documented API contracts between these two tech stacks, there is often inconsistency that you see in like typical ML blogs, which is offline, online feature discrepancy, or some sort of discrepancy between the logic between what the two sides are trying to do. So for example, let's say we launch like a new ranker model in like the Python service, and all of these products are then sent back to the Ruby tech stack, where another engineer can completely override it without the ML engineers knowing all of this and so on, right? So this wasn't great for the organization. This wasn't great for the velocity. Oftentimes, even debugging the simplest of problems required like 2 or 3 engineers from different teams sitting together and debugging this, right? So there were many other problems and so on as such. Don't have the time to cover that, but in a nutshell, how we solved this is, first of all, super sorry for the complex diagram as such. All we did was we got to like we put on our software engineering hats, and we were like, hey, let's get to more modular system design. I think modular system design has been covered in a couple of talks today as such. So we were like, hey, let's greatly simplify the parts of the system that weren't very visible to the machine learning engineers. So all of the retrieval, all of the ranking, and so on as such were moved on stacks that machine learning engineers were very familiar with, while we kept the search backend in Ruby very, very simple. So, this meant that machine learning engineers had full visibility into their work. They could launch multiple ML models without having to rely on a completely different team to do this and whatnot as such. This was only possible because like we invested in like an in-house ML platform. This is a quick plugin for Griffin, our newly formed ML platform as such. So what Griffin did is it provided us a lot of features that you see in like state-of-art ML platforms or teams, like feature store, continuous training and deployment pipelines, and most importantly, monitoring over all of the models that we have in production, right? I'll conclude the talk very quickly by talking about some of the lessons that we have learned along our journey, right? So the first one is investing in human evaluation data. It will take some time to set up, but once you have human evaluation data over your products or your online signals or like search results and so on as such, it will have fantastic returns. You'll find out problems that you wouldn't typically see through your online systems, right, or online signals. The second one is about the importance of tackling cold start problem. We put this off for very, very long because we were like, hey, they're tail queries. Usually people, like maybe a couple of users only search for them once a while. But once we started investing in like cold start problem or solving it, we really realized that it resulted in a lot of long-term user satisfaction. Users kept coming back to Instacart more and more, especially new users. They activated a lot more and so on as such. So like, I would definitely advise people to start investing in that as soon as possible. Another is like investing early in like model monitoring and alerting. I'm pretty sure you've heard about this in all talks, so I'm gonna skip that. Adopting good coding practices and deployment based practices and so on and such. So just because we are like machine learning engineers doesn't give us excuse to write crappy code or not follow good PR processes and so on and such. So definitely treat yourself as like a software shop and make sure that you follow like the best state-of-art practices in like software engineering, right? This one is in a similar vein as such. Make sure that you maintain like a service runbook. Make sure that you communicate to your partners about like your APIs, your monitoring dashboards, and so on and such. So they trust you a lot more and give you more power and control, so that you can independently iterate on the models that you have and move on with the work that you do and get like really productive. That's all from me today. I'll take any questions now.
Yes. We have time just for 1 or 2 questions. Awesome. Here you go.
Hey, Tejaswi. First of all, great presentation. My question is more related to the autocomplete use case, the model fusion layer that you talked about, where you aggregated the results from different models. Did you assign weights for different models? And if yes, how and how often do you all update those weights based on the new information that comes in?
That's a great question, actually. I mean, like, so initially, as such, we took like a very simple approach. As such, we just multiplied the 2 models. We just calibrated the scores between like a range, within the same range, and then just multiplied the scores as such, which gave us like great wins. But we could not iterate on top of that. And then we tried to use grid search to balance these different objectives and so on and such, and try to just check different online metrics and how that works and whatnot. Again, that had diminishing returns after a while. Right now, we are very interested in trying out contextual bandits, as well as some better multi-objective optimization approaches. There are a few I can chat about that later. Those are showing promises offline. We'll have to see how they translate online. Yeah. Of course.
I think I saw one more hand. Are we good? Okay, awesome. Well, you can also catch them after, correct? You're not going to disappear on us, are you?
Yeah.
Okay, fantastic. Thank you so much.
Thank you.